Welcome to the 9th lecture of the course Discrete-time Markov chain and Poisson processes. Recall that in the previous lecture we have talked about accessibility and communication, and then we talked about closed class communicating classes and closed communicating classes, and then today we are going to discuss about something called heating time. Okay? So, what is heating time? Heating time basically means that when I entered into a subset of the state space. So, the definition of the heating time goes as follows. Suppose A is a subset of S is our sample state space. So, A is a subset of the state space. So, if I have this is the state space and suppose this set is A. Okay. This set is A, this consists of some states, maybe it can consist multiple states, it may consist single state, I mean anything is possible. Now, the heating time Ta is nothing but defined by this particular equation. What is this equation? Let us try to understand what this means. So, first consider this set. What is this set? I am taking the collection of all possible values of n greater than equals to 0. Of course, n are integers in our case, n is greater than equals to 0 such that xn belongs to A. So, maybe x naught is here, then x1 is also here and x2 enters here, x3 is here, then maybe x4 comes out of the set. So, in this particular example, the set, this set will look like something like 2, 3 and maybe then x4 is outside, x5 may be inside, so 5 and so on so forth. Something will come based on the chain, okay, based on the chain, whether the chain is inside the set A or outside the set A, based on that some set will come. Okay. So, I am taking the collection of all possible values of n such that xn belongs to A, that basically I am considering that particular set. Now, I am taking the infimum of that set. So, when I take the infimum, in this case if I take the infimum here, that turns out to be 2. So, what is that? Intuitive, I mean that basically mean if I start from outside, if the chain start from outside, this 2 is basically nothing but the time at which I entered, the chain enters the set A for the first time. Okay. So, that means that the heating time is nothing but for the first time when the chain enters to a particular set under consideration, if the chain starts from the outside. And of course, if the scenario is like that, if this is my A set and if x naught is inside, then of course, this set will consist 0, this set will have 0 in this particular case and the infimum will also be 0. So, T A will be 0 in this case if I start from inside A, because in this case 0 will be there and I am taking the infimum. So, infimum is basically in our case is nothing but the minimum element of the set. So, that is why T A will be 0 in this case, but T A will be 2 in this particular case. So, that 2 points are mentioned here, that well, if I start from A, T A has to be 0. If I start outside A, then T A is the first time when the chain enters the set A after the time 0. Okay. It is the first time when the chain enters the set A after the time 0. Okay. So, these are basically the definition. Now, you see that I have written one convention here, that infimum of phi equals to infinity. Why this convention we need to take? First of all, that we need to take because suppose something happened like that, this is my S and A is here and chain is starting from, suppose this state is x naught and this state is like that, from this state I cannot go to A. So, any state in A is not accessible from this particular state. Suppose any state in A is not accessible from this particular state, then of course if I start from this state, if the chain starts from this particular state, I will never visit the set A and that says that this set will be phi in this case, because for any n xn does not belongs to A in this particular case. So then this set will be phi, and that means that starting from this particular state, I will never visit the states in A. Okay, I will never visit the states in A, the chain will never visit the states in A, and that basically means that in any finite time I will not reach A. And that is why the convention is taken that when this set is empty, that means starting from something I cannot visit the state A, then the heating time is taken to be infinity. That means that infinity time I will hit that. That means basically in practice I will never go into the set A. Okay, so this is the definition of the heating time. It is basically nothing but infimum of the set n greater than equals to 0, such that xn belongs to A, and with the convention that infimum of phi equals to infinity. Then we have 2 points that, well, if x naught belongs to A, then Ta has to be 0. This is the scenario in this case, and if x naught does not belongs to A, this is the scenario in this case. Then Ta is the first time after 0 when the chain enters the set A. Okay, so now let us see that notation that, well, if A is singleton, then I suppose my A is, in this case A is singleton I, then I can write T instead of A, that singleton I, that is basically nothing but this. But for simplicity, instead of writing this notation, we will write this one. Okay, this curly bracket we will not put here. The curly bracket we will not put here. We will just use this notation. This is the merely a notation. Okay. Now, one of the very interesting thing is that to see this probability. What is this probability? Ta is finite. So that means in the finite time I will be in the state A when I start from 0. So this I can write as Ta less than infinity given x naught equals to I, because here I am starting from I. So starting from the state I, what is the probability that I will visit any state inside the set A in a finite time? This probability in many practical scenario is very meaningful. So in this particular lecture we are going to talk about this kind of probability, and through some example we will show that how we can calculate this probability for different kind of problems. Okay, so the probability that starting from I, the Markov chain will ever hit A is given by this probability, and this is the notation we are going to use in this case, that it is nothing but starting from I in finite time the process will hit the state A. Okay, and with our pi notation we can write this in this form, or in the standard notation we can write this in this particular way. And informally in many cases, instead of writing this Ta less than infinity, we will write that hit A. That basically means that Ta less than infinity. So hit A is basically nothing but same as Ta is less than infinity. Now I is there, so starting from I, when what is the probability that I will hit A, I will ever hit A, that basically means that starting from I, what is the probability that the Markov chain will enter to the any of the state in the set A in finite time. Okay, and there is another terminology, that absorption probability. If the A is a closed set, just recall what is the definition of closed set. A set, a communicating class is called closed if I cannot go out from that particular class. Okay, once I am inside the class, I will be there in the class forever. So that kind of class is called the closed class. And if I try to find out what is the probability of hitting a closed class, that is generally called the absorption probability, because once I am inside this class I will not come out of the class. So the thing is that chain is, once chain is entered into the class, the chain will be absorbed into that particular A forever. It will never leave A in future. It will be inside in A forever. So it is as if the chain is absorbed into the set A. Okay, into the set A, and that's why basically this probability, if A is closed, this probability HIA is called the absorption probability. Let us proceed and let us try to see this absorption, that hitting probability with help of an example. So this example is taken from this book, that Norris, book by Norris. The author is Norris, but the name of the book is Markov chain, and this is published by Cambridge University Press in 1997, and this example you will find in the page number 12. So the process goes like that. Suppose we consider a Markov chain with one step transition probability specified by the following diagram. So earlier we have seen that if I am given with a one step transition probability matrix, I can draw a graph corresponding to that probability matrix, okay, that one step transition probability matrix, and where basically the idea was that nodes are basically states, and directed arrow, directed edge actually signifies that I can move from a particular state to another state in one step with some positive probability. Now in this case you see that with that edges, nodes and edges, now I have another thing, I have written some numbers here. What are these numbers? These numbers are nothing but what is the probability. So in this case you see from 1 I can go to 1 only, so and that can happen with probability 1. So from 1 I can go to 1 only, from 2 I can go to 1, I can go to 3, and from 2 I can go to 1 with probability half, and to 3 with probability half. So these are the probabilities. The directed edge actually tells us from 2 I can go to 1, and this quantity tells us that what is the probability of going from 2 to 1 in one step. Similarly from 3 I can go to 2 with half probability, and from 3 I can go to 4 with probability half, and from 4 I can be in 4 only, and that is with probability 1. Now you can see that I can very easily write the probability matrix in this case from this diagram. So I have the state 1, 2, 3, 4, 1, 2, 3, 4. So 1 to 1, that is 1, rest of them are 0. From 1 I cannot go to any other state in one step. From 2 I can go to 1 with probability half, and 3 with probability half, rest of the probabilities are 0. From 3 I can go to 2 and 4 with the equal probabilities, rest of them are 0, and from 4 I can go to 4 only in one step, and rest of the states are not accessible in one step from 4. So given this matrix I can draw this diagram, and given this diagram I can write this matrix. So this diagram and matrix has a 1-to-1 correspondence. Given the diagram I can draw, I can write the matrix, given the matrix I can draw the diagram, okay. So that means this diagram actually specifies the one step transition probability matrix of a Markov chain. Now what we are interested in this case, to find out starting from 2 what is the probability of absorption in 4. We are interested to do that. So starting from 2, I start from here. Now what is the probability of absorption in 4? Note that if I can go to, from 2 I can go to 1, and once I reach 1 I will be here forever. On the other hand, from 2 I can go to 3 and then maybe go to 4 in some steps, and once I go to 4 I will be here, the chain will be here forever, it will not come out of the state 4. Okay. So we try to find out the absorption probability in this case, absorption probability in 4 starting from 2, that is basically the idea here. And as we proceed we will see that using, I can write some linear equations, and solving those linear equations I can able to find out the required probability. Okay, we can write some system of linear equation, a system of linear equations, and by solving that system of linear equations we can actually find out the required probability in this particular case. So how can we proceed? Let us proceed. So we denote this Hi is that probability. Instead of writing 4 here, that I am not writing anymore. So just make the notation little bit simple. I just use Hi is equals to probability that Pi of Pi that I hit 4. Okay, Pi that I hit 4, that basically mean that it is nothing but probability that I hit 4, that T4 is less than infinity when I start from the some state I. Okay? And in particular we try to find out what is H2 that we want in this case what is H2. Okay? We want the value of H2 because I equals to 2 is basically starting from 2, what is the probability that I will reach the state 4 in finite time, and once I reach state 4 I will be absorbed here, I will not come out that particular state 4 for this particular Markov chain, because from 4 I can only remain in 4 with probability 1, I can remain only in 4 with probability 1. Okay? Now the next point is very simple from here. First point is that H1, what is H1? Starting from 1, what is the probability of hitting 4? Okay, what is the probability of hitting 4 in finite time? Now if I start from 1, I will be in 1 forever, I will not come out of 1 in this case. So clearly H1, the probability of hitting 4 starting from 1 will be 0, H1 will be 0. Similarly H4 will be 1, because if I am once in the 4, I am already in the 4. So that in finite time I will hit 4 with probability 1. So that why H4 is equals to 1. Okay? So H0 is 0, H1 is 0. The reason is that once I am in 1, I cannot come out from 1. So in finite time I will not visit the state 4. So clearly that probability that visiting state 4 in finite time starting from 1 is 0. Similarly, if I am in 4, I start from 4, I am already in 4. So in finite time I am already in 4. So that means basically T4 will be 1, because with 1 probability in finite time I will be in 1. Okay, I will be in 4. So these two are very easy to see from this diagram, that okay, H1 has to be 0 and H4 has to be 1. Okay. So what we have done here, basically use a new notation HI just to make it little simple. I do not want to write 4 in the superscript in power here, and then basically easy to see that H1 will be 0, because once I am 1, then I will not come out from 1. And so basically in this case I can write in this way also, T4 will be infinity if we start if x naught equals to 1. Okay, if x naught equals to 1, T4 equals to infinity. So in finite time I will not visit 4. So that means basically in this particular case H1 will be 0. And why T4 is infinity? Just recall the definition of T4. T4 is basically nothing but infimum of the set n greater than equals to 0, such that xn equals to 4. xn equals to 4. Now in this case you see that if I start from x equals to 1, for any n, xn will not be 4. So that's why basically this set is 5. If I start from 1, this set is 5, and so T4 is infinity. Similarly T4 is equals to 0 if x0 is equals to 4, because for 0, that 0 element is in this set. Okay, now 0 element is in this set, so when I take the infimum, that will be 0. So in this case in finite time I will not reach 4. So the probability of reaching 4 in finite time starting from 1 will be 0, and in this case the time is 0, T4 is 0, so that is finite in fact. So starting from 4 I will reach 4 in finite time and in 0 time, and that's why that probability, the probability H4, this probability is 1 when I is equals to 4. Okay. So this is basically the idea behind these two. Now let us proceed and let us see how I can solve for other values of I. So I got H1 which is 0, I got H4 which is 1. Now in between I have H2 and H3. I have to find out what are these two values. Okay, I have to find out what are these two values. Two extremes we have find out in this case, and in between I have H2 and H3, and I try to find out what are these values, and in particular in this case I am interested in H2 only. Okay, because I try to find out starting from 2 what is the probability of absorption in 4. So that means I am basically interested in H2. So now the thing is that you see that H2, which is this is basically probability that in finite time I will be in state 4 starting from 2. Okay. Now, using the conditional probability, I can write it T4 is less than infinity given x 0 equals to 2, x1 equals to from 2 I can go to 1. Okay. So, 1 multiplied by probability that x1 equals to 1 given x0 equals to 2 plus some quantity. So, plus I will read I can write here is that plus probability that T4 is less than infinity given x naught equals to 2, x1 equals to 3 multiplied by probability x1 equals to 3 given x naught equals to 2. Okay. So, what I have done, note that from 2 I can go to 1 or I can go to 3 in this case in one step. So, what I am doing is that I am doing the conditioning with respect to the next transition. Okay. I start from 0, the next transition can be 1 with probability half, it can be 2 with 3 with probability half. So, I am conditioning with respect to the next transition, and when I am doing that, what I have written is that first is 2, then the next is 1, and then the probability that what is the probability of going from 2 to 1 in one step, plus the first is 2, that 2 is kept here, the second can be 3 and multiplied by the probability that what is the probability that I can go from 2 to 3 in one step. Okay. So, conditioning on the first transition, I can write that H2 in this particular form. So, if I can go from 2 to another state, that the contribution of that particular state I have to add. So, if I can go from 2 to maybe m number of states, then there will be m such additions will be there, m such terms need to be added, and then I can write H2 equals to this plus this plus this, so on and so forth. In this case, from 2 I can go to 2 states, so 2 contribution, 2 terms comes here. Okay. Now, look into this first probability. If I look into this first probability, you see that we have discussed this one, that Markov property tells that if I know the state of the Markov chain in some time, then the Markov chain start from there afresh. Okay. If I know the Markov property tells us that if I know the states of a Markov chain at some point of time, then the Markov chain start from that time afresh. So, I can forget the previous part of the Markov chain, I can think that the Markov chain is at that particular state. So, the Markov chain, suppose sometime the Markov chain is in the state 1. Okay. So, in this case, the first time point it is state 1. So, I can now think that well x naught I can remove, and I can think that well x1 is the starting point and the Markov chain now start from 1. So, the initial distribution is delta 1 and it proceed. Okay. Initial distribution is delta 1 and it proceed from that particular initial distribution and so on and so forth. I can forget the previous part completely. Okay. So, that means that in this case I can ignore this one. Similarly, in this case I can ignore this one. These two terms I can ignore, and now I can write this quantity same as probability that T4 is less than infinity given x naught equals to 1. Again I can write x naught equals to 1 because Markov chain starts from there itself. Okay. Markov chain starts from there itself. So, it is again starting point, I can write x naught or whatever you can write x1. So, it is basically again starting from that particular point that is basically important. So, I can write x0. Okay. And then multiplied by p from 2 to 1 in one step plus probability that T4 is less than infinity starting from 3 multiplied by p 2 to 3 in one step. Okay. So, we can write this way that it is basically probability that I will visit the state 4 in finite time given h naught equals to 1 starting from 1 multiplied by p to 1 multiplied by p to 1, it is the one step transition probability from 2 to 1 Similarly, visiting the state 4 in finite time starting from 3, that probability of that event multiplied by one step transition probability from 2 to 3. And now the first quantity is H1, because starting from 1 I am visiting the state 4 in finite time, and the second this probability is basically H3, and then P21 is half, so that half comes here. P23 is also half, so half comes here. Okay, so conditioning on the first transition, I can write H2 is same as half H1 plus half H3 in this particular case. Okay, so we wrote this one. Similarly, for H3 also I can write, from H3 I can go to 2 and I can go to 4. Now, so that means with half probability H2 and with half probability H4. Okay, so H3 equals to half H2 plus half H4. So now I have some system of equation, along with I have H1 equals to 0, H4 equals to 1. Now I have to solve this set of equation. I have to solve this set of equation, and then I can find out the value of H2 as well as H3, and once I have that, I am done. And as our particular aim is to find out H2, so let us start with the first equation. So H2, as we know that H1 is 0, so that term does not contribute anything. I have H2 equals to half of H3, and then H3 I can write from here. So H3, again this quantity is 1, so H3 is basically half H2 plus half. Okay, H3 equals to half H2 plus half. From here I just plug in here. Now I have a equation in H2. I can solve for H2, and if you solve, if you will find it is nothing but H2 equals to 1 by 3. So we got that H2 equals to 1 by 3. We can also find out what is the probability of H3 in this case. That is not at all difficult, because H3 is basically nothing but half H2 plus half. So it is 1 by 6 plus half. So that basically mean that 3 plus 4, 4 by 6, which is 2 by 3. Okay, which is 2 by 3 in this case. So H3 is 2 by 3, H2 is 1 by 4, and H1 is 0, H4 is 1. So let us try to interpret this result. What does this basically tells us? That if I start from 2, there is a 1 by 3 probability that I will visit the state 4 and infinite time, and once I visit the state 4, I will be there forever. If I start from 3, there is a chance of 2 by 3 that I will be in state 4 and I will be there forever. Okay, and this is very, very intuitive, because if I start from 2, then I have to basically first go to 3 and then go to 4, and on the other hand, in one step I will go to 1. So there is a less chance of absorption in 4 compared to if I start from 2 compared to if I start from 3. Okay, there is the less chance of absorption in 4 if I start from 2 compared to if I start from 3. That is intuitive, because from 2, 4 is far ahead, whereas 1 is close enough. If I go to close, I will be stuck there. On the other hand, from 3, 4 is closer compared to 2, and so that probability is higher. Okay, so this is basically the way we can find out the heating probability. And you see that the basic idea is that we write the set of linear equations with some initial conditions maybe, and then we try to solve those set of linear equations to find out the required probability. Okay, let us proceed and let us now put that everything in terms of a theorem. Okay, so the theorem goes like this: the vector of heating probabilities H consists of HIA. So basically, if I have a state space S, then basically like in this case, I have 4 H values: H1, H2, H3, H4. So taking everything together, I am calling it H. Okay, so how many states are there? I have so many HIs there, HIS there, and taking everything together, I am calling it H. So that is a vector. Okay, So the vector of hitting probability is this, is the minimal non-negative solution of the system of linear equation this. So few things I need to discuss here. One is what do we mean by minimal, what is non-negative, and how we get this system of equations. So the way we get this system of equation is exactly same what I have discussed here. Okay, what I have discussed here, through this I got this one. So if I am already in A, if I start from A, I is the starting point. If I am already in A, then I am already in A. So in finite time anyway I will reach A. So I am in A. Okay. So basically if I belongs to A, then TA is 0. So if I start from A, then TA is 0. So that says that probability that TA is finite starting from x naught equals to I is 1. Okay, and this is basically HIA. So if I start from A, HIA is 1. So 1 comes from there. If I am outside A, what happens? If I does not belongs to A, then that transitions I will make, that this transition I will make, that first transition I will make, and suppose from I, in the first transition I can go to J. So it will be Pij multiplied by 8Ja. Now starting from J, what is the probability that in finite time I will hit the set A? Okay, so that probability comes here. So it is Pj multiplied by 8Ja, and the sum I need to take over all possible values of J in the state space. Okay. So these two equations comes from this one, as well as the understanding that once I am in A, I am in 4, that H1 is H0 is 1, H4 is 1. So that from that two thing, these two are coming. The only thing is that, well, in this case I am considered the singleton set, but it may be the A can have multiple states. A can have multiple states. So I have written these two things to they are this way. Okay. So this way we got this system of linear equations. Now I have to solve this linear equation. So when I solve the system of linear equation, there are few possibilities are there. There could be unique solution, there could be infinite solution. Not only that, the solution can be positive, can be negative. The solution can be positive, can be negative, means that in this case when I solve this one, Hi can take the solution of this system of equation, can take, some of them can take positive values, some of them take negative values, all can take positive values, all can take negative values, everything are possible. Okay, all can take 0, some non-zero, all those possibilities are there. Now because HIA are probability, so probability cannot go outside the range 0 and 1. Okay, so that means I have to take that solution which give me all the component of the H vector to be non-negative. Now if there are multiple non-negative solutions, which one I need to take? It says that this theorem says that I should take the minimal non-negative solution, the minimal solution. Among all the non-negative solution, I take the minimal solution. Now the question is that what is this minimal? This minimal basically means this. So if suppose I have another solution xi, okay, I have another solution x consists of xi, I belongs to S, and this is a non-negative solution. So that means that xi's are greater than equals to 0. Okay, for all I. Now the minimality mean that that solution I will take for which any other solution is greater than or equals to that particular solution xi. Okay, so H will be minimal, this H will be minimal non-negative solution if all the HI's are greater than equals to A, and for any x which is a solution of this system of equation, non-negative solution of this system of equation, xi is greater than equals to HIA. Okay, if this condition is satisfied, then we say that H is minimal, H is non-negative because all the HI's are greater than equals to 0, and that particular solution of this system of equation I am going to take as the values of HI's which are given the probability that hitting the set A starting from I. Okay, starting from the state I. So with that, let us move on and let us see. Okay, one thing I should discuss here, that in this case you see that I have not talked about the minimality here. So from where the minimality comes, you see that H0 equals H1 equals to 0, that particular condition is not given by this set of equations. You can check that H0 H1 equals to 0 is not given by this particular set of equation, because in the previous example A is 4, A is the singleton set 4, so it says that A 4 and then 4 is basically 1. From here A is 4, and then H2 I can write as half H1 plus half H1 plus half H3, because in this case basically I have taken I to be 2 and I to be 2 does not belongs to the set A, because A is having singleton 4. H3 4 I can write as half H2 4 plus half H4 4. Again in this case I is 3, which does not belongs to A, What about H1? H1 4, again 1 I equals to 1, that does not belongs to A, but the problem with that is that from 1 to 1 I can only go, so it is basically 1 times H1 4. So this actually is not giving me any constant, it only saying that H1 equals to H1, H1 4 equals to H1 4. So that's why this is not giving any kind of condition there. So now because H1 4 is a probability, it has to lies between these two. Now what is the minimal value? Minimal value is H1 equals to 0. Minimal value, when I talk about minimal value is nothing but H4 equals to 0, and that actually we have taken here, but from another point of view, that if I am in 1 I will never visit 4. From that point of view we have taken H1 equals to 4, but through this minimality also we can reach the same conclusion in this case. With minimality also we can reach the same conclusion in this particular case. Okay. So with that we proceed, and maybe we see now another problem where we can try to find out that absorption probability, and we can do this one using the using this stated theorem. Okay. So this is basically the gambling model, and we have already discussed the gambling model. It is basically nothing but a gambler went to a casino and start playing, and initially the gambler has maybe rupees I. So gambler has rupees I, rupees I, and he went to the casino and he start playing. How the place goes? Place goes like this, that if the gambler wins, then he will gain 1 rupee. So if the gambler win in the first game, if he win, he will have I plus 1 rupee, and if he lose, then he will has to pay the casino 1 rupee. So now he will have I minus 1 rupee, and the probability of win is P, and probability is lose is Q, and P plus Q has to be 1. Okay. So that means from I the state can go to I plus 1 with probability P, that is the winning probability, and from I the state can go to I minus 1 with probability Q, which is the losing probability. And there are two end point, because if the gambler loses his or her all money, then the gambler has to leave the game. That means gambler will be in the state 0, and on the other hand gambler fix some rupee n, and if he gains the rupee n, then he will stop the play there, he will quit the play there, and he will go back home. So once he reach n, then he will be the state n forever. Okay, he will be the state n forever. That's why that from 0 I can go to 0 only, because he cannot play, he is forced to leave the game. On the other side n, he decided to leave the game once he have n rupees of n rupees in his hand. Okay, so he start with some I in between, he can go any side. Once he reach 0, he is forced to leave the game. once he reach n, he is basically by will, he is basically leaving the game. Okay. So these two are basically with one probability, and in between that the probability of going towards right is p, probability of going towards left is q in one step. Okay, one step right, one step left in one time step is p and q respectively, and then of course p plus q has to be 1. Here p plus q, we have taken p plus q has to be 1. Also we take that p is greater than 0, so it is a both side you can go. Okay, both side you can go with some positive probability. Okay, I have written this thing here. Now if you write in this thing in mathematical notation, this is the way we can write in mathematical notation, that p00 is 1, p11 pnn is 1, so these two are 1. Then pi to I plus 1 is p, pi to I minus 1 is q, and this is true for all I in between except 0 and n, except 0 and n, this is true for all I. So I equals to 1 to n minus 1, this is true, and for any pij it is 0. From I cannot go to maybe I plus 2, I cannot go from here to here in one step. In one step I cannot go. Okay, in one step I cannot go. So all the pij's are 0 in this case. So now one of the things which I can look into in this case is that what is the probability that gambler broke? That means gambler lose all his money. So what is the probability that the gambler starting with an initial fortune I, here fortune means the rupee I, goes back bankrupt. So he loses all his money. So he started from here some I, and he basically reached this state 0 before reaching the state n. Okay, because once he reach state n, he will reach. So once he reach n, he will never reach 0. So I try to find out what is the probability that the gambler reach the state 0 before reaching state n. Okay, and so that means gambler bankrupt. So it is a very well question to ask. Suppose I go to a casino with some money, and I may ask this question that what is the probability that I lose all my money? Okay. On the other hand, I can also ask this question that what is the probability I can actually reach the state n, that means I reach my target. These two probabilities of course I can ask to myself before playing any game in the casino. If the probability of bankrupt, probability of losing everything is very high, then I should not play that game. On the other hand, if the probability of losing everything is not very high, I can test my luck. Okay, I can test my luck in that particular game. So these kind of probabilities are very meaningful to ask in this particular kind of setting. Okay, so let us see how we can solve. I can find out these probabilities, and the way to do this one, again writing the set of linear equations. So now in this case the A set A is basically singleton 0. So again I am not writing 0 here again and again to have this notation, simple notation. So that basically mean that, well, this hitting probability to 0 starting from I write it hi. Now h0 equals to 1 because of this condition that if I in A, then HIA is 1. So h0 is 1 because in this case I is equals to 0, which belongs to A, which is basically our singleton set 0. Okay. Now if I is not equals to A, if I is anything between 0 to n minus 1, then of course this I does not belongs to A. This I does not belongs to A, and then I try to write the linear equation, and in this case writing the linear equation is very simple because I start from hi. Now from hi what happens, that I start from I, what happens from I, in one step I can go to I plus 1 or in I minus 1. And these two probabilities I know, what is the probability of going to I plus 1 and what is the probability of going to I minus 1. So from I can go to I plus 1 with probability p, and once I am in I plus 1, now I need to find out what is the probability of hitting 0 starting from I plus 1, which is hi plus 1. Similarly from I can in one step I can go to I minus 1, which probability is q, and now I need to find out from I plus 1 starting from I minus 1 what is the probability of hitting 0. Starting from I minus 1, what is the probability of hitting 0, which is hi minus 1. So we have written the set of linear equations for I equals to 1 to n minus 1. What happens if I take I equals to n, which also does not belongs to A, and in this case basically Hn is again from n, I can be in n, so it is nothing but 1 multiplied by Hn. So that means again this linear equation is not giving me anything, so I have not written this linear equation here. Okay. Now you see that how many linear equations I have here. Here I have 1 which is giving me h naught equals to 1, and here I have n minus 1. So I have finally n linear equation. Okay, I have finally n linear equations, because this one I am not considering, because this is not a equation as such, it is only saying Hn equals to Hn. So this is not giving me any constraint. Okay, so this one I am not counting, except that I have n linear equations. Okay, how many hi's are there? For each state I have a hi. So how many states are there? I have from starting from 0 up to n, so I have n plus 1 hi's. Okay, I have n plus 1 hi's. So that means I have n equations, I have n plus 1 variables to find out. So clearly one of the variable is a free variable. So normally what we do when we solve the set of linear equations, if we have more variables than the number of equations, we take some of them, we take as a free variable. Like if I want to solve x1 plus x2 plus x3 equals to 0, and a 2x1 plus 3x2 plus 3 x3 equals to 0. If I want to solve this set of linear equations, we have basically 2 linear equations, 3 variables. So we can take one variable as a free variable, and we can solve other 2 as a function of the free variable. Okay, so in this case also I can take one variable as a free variable, that there are one extra variable compared to number of equations. So one variable I can take extra variable, and that I can take Hn. Okay, that I can take Hn, and so again notice that Hn can take a value between 0 and 1. So if I need to take a value of Hn, that has to be a minimal value because of this minimality condition here, and if I take this one, that means I have to take Hn equals to 0 only. So that's what I have written here, that since Hn lies between 0 and 1 and we are interested in minimal non-negative solution, we must take Hn equals to 0. Okay, we must take Hn equals to 0. So now finally what I have, H1 equals H naught equals to 1 I have, Hn equals to 0 I have. Now I have to solve for Hi for I equals to 1 to n minus 1. Okay, so now let us go for this solving. Okay, so what we can do from here is that, see, we have the constraint that P plus Q equals to 1. So I can write P plus Q here. Okay, I can write P plus Q Hi equals to P Hi plus 1 plus Q Hi minus 1. Now you see what I can write from here. Now if I keep the P term in this side, it is Hi minus Hi plus 1 is equals to Q times Hi minus 1 minus Hi. So what I have done, P times Hi I keep in this side, this P times Hi plus 1 I take to the other side. So I have minus P times Hi plus 1. In the similar manner, I keep Q H minus 1 in this side, and Q into Hi I take the other side, which gives me the minus Q Hi. So I get this particular equation, and this kind of equation is generally called difference equation. So I get this difference equation, that this one is nothing but Q by P into Hi minus 1 minus Hi, or I can also write from here this Hi minus 1 minus Hi is same as P by Q Hi minus Hi plus 1. both of them I can write. Okay, one in this case what I did, this P I take the other in this side, or in this case what I take is that Q I take on the other side, divided by Q in this side. Okay, so both of them we can write, and what we can do is that in this case we take this particular form. Okay, we take this particular form, and from this particular form, so what I can write, let me write this is in the next slide, that so we get this particular expression. Now this is true for different values of I. Now we will put different values of I. If I put I equals to n minus 1, we get exactly this equation, that if I put I equals to n minus 1, so this become n minus 2, this is n minus 1, this become n minus 1, and this become n. Okay, then I put I equals to n minus 2, I get this equation. In this way I proceed. Finally, if I put I equals to I plus 1, I get this particular equation, and if I put I equals to 1, I get the final equation. Okay, so putting different values of I from 1 to n minus 1, we get these equations. Okay, now look into the first equation. We have noticed that h n is equals to 0, h 1 equals to h 0 equals to 1. Okay, this we have. So if I put h n equals to 0 here, this quantity become P by Q h n minus 1. Okay, so we get this quantity same as P by Q h n minus 1. Now look into the second equation here. Second equation is that h n minus 3 minus h n minus 2 is same as P by Q h n minus 2 minus h n minus 1. Now this this quantity is same as this quantity here. So I can just plug in this value here, and I get it that it turns out to be P by Q whole square multiplied by h n minus 1. Okay, this quantity I replace by this one, and I got this one. And similarly I can proceed. Finally in general I get that hi minus hi plus 1 turns out to be this quantity. So this power of P by Q actually increasing, power 1, then 2, then so on, it is increasing, and along with this h n minus 1 go on, and finally the term turns out to be P by Q whole to the power n minus 1 multiplied by h of n minus 1. So we have this system of equations, and we are trying to solve it. Now what will happen if I add these equations? If I add these equations, what happens? Let us see. So if I add, first notice that this term cancels with this term. Similarly, I have another equation here. For that, this one cancels with this. So on, proceed, and finally this one also cancels with this term here. I have an equation here, the previous equation, these two term will cancel. So all the term cancels except this term remains there and this term remains there. Okay, this term cancels with this term cancels with the similar term in the next equation, this term will cancel with this term will cancel with the similar term in the previous equation. So finally I am left with hi here, let me write, and I am left with this one minus h n minus 1. And what is this side I am left with? I am left with P by Q plus P by Q square plus so on so forth. Finally P by Q whole to the power n minus I minus 1 multiplied by h n minus 1. Okay, that's what I am left with now, and exactly that's what I have written here. Exactly that's what I have written here, that hi minus h n minus 1 is same as sum of this term multiplied by h n minus 1. That's what I have written here. Now this h n minus 1 I take on the other side, so 1 comes here, and then I have this. Now this one is a geometric sum. Now this one is a geometric sum. We can do this sum, but there comes two cases. First case is that if P equals to Q. Okay, if P equals to Q, that means this quantity is 1, this quantity is 1. So P equals to Q, that basically because now P plus Q is equals to 1, this implies that P plus Q equals to 1 basically implies that P equals to Q equals to half. So that's why I have written P equals to half. If P equals to half, that means Q is half. So in this case P plus Q is 1. So in this case what we got is that I have n minus 1 terms are there. I have n minus 1s are there. So if I add n minus 1s, that will give me n minus I. So I have n minus I here multiplied by h of n minus 1. Okay. And when P is not equals to half, what we got? If P is not equals to half, we got this quantity, and this comes from the geometric sum. So we know that if I have a square, a cube, so on up to a to the power n, that sum is nothing but 1 minus a in the denominator and 1 minus a to the power n plus 1 in the numerator. Okay. So the power is basically number of terms here, that is basically the power. So exactly that's what I have done here. Here the number of term is n minus I. So 1 minus p by q whole to the power n minus I divided by 1 minus p by q. So p by q plays the role of a in this case. Okay. So this hi I got this way, and each hi and this is true for any I from 0 to n minus 2, and so any h, so h0 to h n minus 2, all of them we have written in terms of h n minus 1. Okay, h0 to h n minus 2 we have written in terms of h n minus 1. Now recall that we have one condition that h1 h0 is 1. Now if I take h0 equals to 1, that basically give me from here is that if p equals to q, if p is not equals to half, first take the first case, that h0 equals to 1, this actually implies that 1 minus p by q whole to the power n, instead of I put 0 here, divided by 1 minus p by q h n minus 1 equals to 1. Okay. From that I can solve for h n minus 1, which is nothing but the reciprocal of this. So 1 minus p by q divided by 1 minus p by q whole to the power n. Okay. So that's what we can write, and once we write this one, I can plug in that value here, and once I plug in, this quantity cancels with this quantity. I am left with 1 minus p by q whole to the power n minus I divided by 1 minus p by q whole to the power n. That's what written here. Okay. Similarly, for p equals to half, we can proceed. P equals to half, h0 is basically from here nothing but n times h n minus 1, and this has to be 1. This says that h n minus 1 has to be 1 by n. So that means if I again plug in that value here, it basically turns out that when p equals to half, hi is nothing but 1 minus I by n. Okay, p half, for p equals to half, hi equals to 1 by 1 minus I by n. So this way we can able to find these probabilities. This way we can able to find these probabilities. Now let us see this probability little carefully. So recall that. Okay, so suppose let us take about p equals to half first. Okay, let us talk about p equals to half first. So if p equals to half, that basically mean that if p equals to half, that basically mean that if you increase n, what will happen? This quantity will be small. Okay, so hi will increase. So if I increase n, then hi also increases, because this quantity will be small. So this quantity also increases. Not only that, hi goes to 1 as n goes to infinity. Okay, what does this mean? What is n? N is basically the target the gambler fix. So gambler, if the gambler is very greedy, then if the winning probability is half, then gambler will actually finally broke. Gambler will lose everything. So when we go for gambling, we should not fix our target is very high, because if we fix this is very high, there is a high chance that I will go broke, I will lose all my money. Okay, that is basically told by here when p equals to half. Moreover, when p equals to half, again you see that if I have more money, initial money is more, if I increases, then hi decreases. If I increases, hi decreases. Okay, so that means if I am rich, then basically there is a less chance of losing everything. If I am poor, there is a more chance of losing everything. So that are very intuitive, that if I go with lot of money, there is a last chance I will basically finally I will come back with lot of money. But if I have very small money, there is a chance that I lose quickly, I lose those money and I am just broke, I have to come back empty handed to my home. Okay, and this is not conclusions is not only true for p equals to half. Even if I take p is not equals to half, you can see the same conclusion hold true in this case also, that hi goes to I write in this manner, that suppose now pi is less than 1. Suppose now pi is less than half. Now suppose pi is less than half, which is generally case in any casino, that winning probability are smaller. In this case also you can see that this quantity goes to 1. Why? Because p is less than half, that means p by q, this basically implies that p by q is less than 1. So p by q is less than 1 and n goes to infinity, so this quantity goes to 0, this quantity goes to 0, finally hi goes to 1. Okay, so hi goes to 1, so that means that when winning probability is less compared to losing probability, which I mean that if the losing probability, that broking probability goes to 1 as n goes to infinity. Again the same conclusion, that if I am very greedy, there is a chance that I will go broke. There is almost sure that I will go broke. Okay, I should not be very greedy. Okay, so and if p is greater than half, then of course I have some probability of winning, even if n goes to infinity, that hi goes to some l which is greater than 0, which belongs to 0 1, maybe I write which belongs to 0 1 as n goes to infinity. That l you can easily find out from the standard logic of limit, standard limiting thing you can do and you can find it out. So that is the final takeaway from this problem, that how we can solve this problem, that is one takeaway. And then the next takeaway from this problem is as follows, that if I am greedy and if the probability of winning is less than or equals to half, then I will almost sure that I will go broke, I will lose everything. If I am not much greedy, then there is some positive probability of winning and not losing everything. And in most of the casinos, that p is actually less than half, that means winning probability are less than half. And so in most of the casinos is I am too greedy, I will lose, most likely I will lose everything. And if I have more fortune at the initial stage, I have more money at the initial stage, there is a high probability that I will not go broke compared to if I have less amount of money at the initial stage when I am going to the casino. Okay, with that I stop, and in next lectures we will see some more one more examples of such kind. Thank you for listening.